this lesson, I'm going to expand on reaction orders, and we're actually going to look at how concentrations can be plotted in order to anticipate if a reaction is first order, second order, or zero order. So the first reaction order I'm going to look at is first order reactions. Now this is the linear equation for representing a first order reaction. The natural log of the concentration of AT, which simply represents the concentration of one of your reactants at a specific time, equals negative KT, K being your rate constant, plus ln of A naught, and A naught being your initial concentration. So the concentration at the start is going to be A naught, while the concentration after a specific amount of time is going to be AT. And so as you can see here, the linear equation that I have above mirrors y equals mx plus b. And so what you can see is since y is ln of AT, that's going to be on your y-axis, and time is going to be your x-axis. So if you have a first order reaction and you plot the natural log of the either concentration or the pressure, we're going to be interchanging between those very fluidly, versus time, so natural log of pressure or concentration versus time, that's going to produce a linear negative slope. If it does that, you have a first order reaction. If it doesn't, then you do not have a first order reaction. Notice the graph on the left-hand side, graph A. Notice if you just plot pressure or you just plot concentration, then you're going to have a curved slope if it is a first order reaction. So we actually can use this by taking data which we'll get in the lab and plotting it, and if the natural log of that reaction creates a linear negative slope, then you know you have a first order reaction. So let's actually use this equation to solve a problem. So it gives you this reaction right here, tells you it's first order, and then it asks you if the initial pressure of that is 135 torr, what is the pressure after 1,420 seconds? Well, I'm going to use this equation right here. I'm solving for AT. I know what my K is. It's given to me. My rate constant is 6.8 times 10 to the negative fourth. I know my T, it's 1,420 seconds. And then I'm going to add to that the natural log of 135 torr, and there's my value. So what you're going to do is you're going to solve for the right-hand side. Okay? And just as a quick review of natural logs, the natural log simply is the log base E. So in order to solve for the concentration of AT, what you need to do is take E and raise it to whatever you got on the right-hand side. Because remember, a regular log has a base 10, natural log has a base E. So E raised to the value on the right-hand side will give you your pressure of AT, which is 51 torr. So this might be a new concept math-wise. If you need help with natural logs, please come in and see me. Just as with the first order reaction, a second order reaction, the rate law can be changed into an equation that relates concentration at the start to the concentration at any other time. And instead of a natural log, now we have 1 over the concentration at a specific time equals your KT plus 1 over your A naught. Notice this is still y equals mx plus b format. So your y for a second order reaction is going to be 1 over AT, your K will be your slope, and then your 1 over A naught will be your B, or your y-intercept. So notice here, instead of having a negative slope, you're going to have a positive slope. So if you look at this graph right here, the one on the right-hand side, when you have, for your y, 1 over your concentration, for your x, you have time. If you produce a positive linear slope, then you have a second order reaction. Notice the reason why I know it's second order and not first order is when I plot ln of my concentration, it produces a curved slope, and therefore I know it's not first order, it's got to be second. For a zero order reaction, this is my equation. Notice it's just concentration equals negative KT plus A naught. So what the graph would look like here is it would be a negative linear slope for just the concentration on your y-axis, not ln of your concentration and not 1 over your concentration. And so if it's a linear negative slope for just concentration on your y-axis, then you're zero order. Zero order means that the rate does not depend on the concentration. So we can determine the half-life of a first-order reaction with an equation, but really quickly, what is a half-life? Well, the half-life is the time required for the concentration of reactant to reach half of its initial value. So here's your equation right here. Notice it's 0.693 divided by K. So your half-life for a first-order reaction only relies on your rate constant, not on your concentrations. In contrast, for a second-order reaction, it does. So we're not going to have a simple equation for the half-life of a second-order reaction, just a first-order reaction. So a couple of quick pieces of information. For the half-life of a first-order reaction, it is independent of the initial concentration. I already said that. It is the same at any given point during the reaction. So it's going to decrease by half in each of a series of regularly spaced intervals. So if it halves in 5 minutes, it's going to half again in 5 minutes and again in 5 minutes. That will not alter. And so if you have a first order reaction, it's very easy to determine half-life. And in fact, the AP, the only time you determine half-life is with first order reactions. The second piece of information is that the half-life for a second order, as I had said, depends on the initial concentration of your reactant, which means it's going to complicate things, and we actually don't determine half-life for a second order reaction.